All right, well, in the interest of time, let's get started. Thank you, everybody, for joining. Today, we have the final IGPP seminar of this term. We have our very own Tyler Pelle speaking to us today. Tyler studied meteorology and applied math at State University of New York, Oswego, up in the north part of the state. He then completed his doctoral studies at UC Irvine last year, studying ice sheets and their response to climate variability. And he is now a Green Scholar here at IGPP. So today he's going to be talking to us about modeling the century scale response of the Totten and Denman glaciers in East Antarctica to enhanced ice shelf forcing. And right before I turn the time over to Tyler, I'll just mention that we will soon have, we already have the schedule for next term lined up, and we'll send out that lineup to you shortly. And also just a reminder to, and I'll put the link in another email, but a reminder to give us your recommendations for next year's seminar speakers. If there's someone you would like to hear from, please let us know who, and we will make an effort to compile that information for the organizers of the seminar next year. All right, so without further ado, Tyler, take it away.
Awesome, thanks, Dan. Yeah, so as Dan said, my name is Tyler Pelle. I'm a Green postdoctoral scholar here at IGPP. I'm mentored by Dr. Jamin Greenbaum, who joined recently as well. So today I'm going to be presenting some of my late PhD work and also the stuff I've been working on since I joined IGPP in October. It's all about modeling the century scale response of Totten and Denman glaciers located in East Antarctica to enhanced ice shelf forcing. So global sea levels have been rising in response to the 20th and 21st century warming trend, and the rate at which the global seas are rising is projected to accelerate through the turn of the century and beyond. So here I've shown time series of global sea level rise running out to 2300 from the IPCC in 2018. And if we follow the high emission scenario, which is shaded in red here, you can see that by 2100, there's about half a meter of uncertainty, and extending out to 2300, this increases to about 3 meters of uncertainty. The IPCC stated that the majority of this uncertainty stems from the Antarctic contribution. And the reason for this is because the models that project Antarctica's sea level contribution lack realistic representations of the physical processes that drive its dynamic change over time. This inset here is from the International Collaborative Project ISMIP6 Antarctica. And this project sought to make an ensemble of sea level projections of the Antarctic ice sheet out to 2100. And so each of these lines is a separate model contribution, and the color corresponds to the high emission climate forcing that was applied in that model. And so extending out to 2100, you can first see that the results of this project show that we're not even sure really what the sign of Antarctica's sea level contribution is going to be, right? The values extend over negative and positive values. And also there's about a 300 millimeter uncertainty in the Antarctic contribution. And because Antarctica contains about 58 meters of global sea level potential, if we want to make accurate and meaningful projections, then we need to constrain this Antarctic contribution. Now, Antarctica is partitioned into 3 distinct regions. We have the East Antarctic Ice Sheet, the West Antarctic Ice Sheet, and the Antarctic Peninsula. So here I'm showing observations of Antarctic mass change from GRACE and GRACE follow-on, and where we have deep shades of orange, or where we see high rates of mass loss. And this is particularly stemming from the Amundsen Sea sector of the West Antarctic Ice Sheet. However, if you turn your attention to East Antarctica, you'll notice that there are some mass loss signals as well, particularly around Totten Glacier, mass loss signals also around the west, a little bit west of Denman and coastal sectors of Wilkes Land. Now, Antarctica is surrounded by the Southern Ocean, and on occasion, warm currents can circulate along the seafloor and melt the underside of these coastal glaciers in a process known as basal melting. And that's one of those key drivers, those key processes that drive change of Antarctica. And so to describe what that is, I'm going to use the figure here. So this is a schematic of East Antarctica. Over the open ocean on the continental shelf, we have shaded the ocean thermal forcing in degrees Celsius. And over Antarctica's floating ice shelves, we have shaded the basal melt rate in units of meters per year. And if we imagine a vertical cross-section taken through Amory ice shelf going from A to A prime, it would look something like this figure on the right, where if we're starting at A, we're towards the interior of the ice sheet, and we have ice that's resting directly on the bedrock below. So we refer to this as grounded ice, And as we move closer to A prime, there's a transition point where the ice lifts off the bedrock and begins floating over the ocean below. This transition point is called the grounding line, and this floating extension of the glacier is called the ice shelf. And so warm ocean currents circulate along the seafloor into what we call the sub-ice shelf ocean cavity. And this is just this oceanic region below the ice shelf. These warm ocean currents melt the underside of the ice shelf in that basal melting process. And this can result in a few things. Either the grounding line, or that transition point, can retreat further inland into the interior of the ice sheet, or we can thin the ice shelf. And ice shelves are really important components of the Antarctic ice sheet system because they act to hold back this upstream grounded ice, right? So if we thin this ice shelf, we lose the back stress that this ice shelf applies. The grounded ice can flow more easily into the ocean, and that would represent a sea level rise contribution from this glacier. And so because of this, basal melting is one of those key processes that drives change of Antarctica. And so if we want to make meaningful projections of Antarctica, then we need to both better understand this process of basal melting and also be able to accurately implement it in transient ice sheet models. So returning back to the figure on the left here, I've boxed Taunton in red here for a few reasons to draw your attention to it. First is that you can see that we have very strong ocean thermal forcing adjacent to Taunton's floating ice shelf. This thermal forcing is driving rapid rates of basal melting that's indicated by this red shading here. And so this is one of the reasons why Taunton is getting scientific attention. And so I'm just going to zoom into this box here so we can take a deeper look. So Totten Glacier has a sea level potential of about 3.85 meters because it drains a subglacial basin nearly the size of California that's covered in ice that's about 2.5 miles thick. So in this box here, we have shaded the surface ice velocity, and you can see Taunton has a very coherent ice stream that drains the inland ice out into the ocean. And the Taunton's grounding line is overlaid in yellow here. And so this thermal forcing is one of the reasons that Taunton has gained scientific attention, but there's another concerning reason as well. And this is because a number of studies have come out that have confirmed that Totten Glacier has retreated hundreds of kilometers inland into this deep subglacial basin and had a very significant sea level contribution under climate conditions that weren't very dissimilar from today. And so this really leads scientists to, like, when we ask questions about Taunton, we're not really asking if Taunton will retreat like it did in the past, but when. In addition, that strong ocean thermal forcing has driven a 1 to 3 kilometer retreat of Taunton's southern grounding zone. And again, the grounding line is in yellow here. And this is important because this southern grounding zone is located along Taunton's main ice stream. So any reconfiguration of the grounding zone here is going to have implications for Taunton's sea level contribution. Lastly, turning to the east, a study by Greenbaum et al. In 2015 found a possible ocean connection between these two floating regions. And so this is important because if warm water can access Taunton's subshelf cavity, then it can induce melting along the entire eastern grounding zone. And so between this past precedent of retreat and the current dynamic changes that Taunton is going through, that makes this glacier one of the key players of East Antarctic change through 2100. Now moving up the coast to the west a little bit, we were here, now we're just right up here. We have Denman Glacier. Now Denman has a sea level potential that's about half of Taunton, but has been undergoing dynamic changes that has the glaciological community pretty concerned as well. In this figure, we have the surface ice velocity where this is all floating ice up here, and this is the grounded ice sheet. And there's been a reported acceleration of Denman Glacier's floating extension here that has been corroborated with a 5 kilometer grounding line retreat that was observed between 1996 and 2018. This retreat is what has us concerned because Denman Glacier is retreating back towards the deepest continental trench on Earth. And a little bit further on into the talk, I'll get into why this is an unstable glaciological configuration. But basically if Denman's grounding line were to continue retreating in this manner, it could lead to catastrophic rates of sea level rise. And so again, I'll jump into that a little bit further, but again, all these dynamic changes that Denman is going through makes it another key player of East Antarctic change. And so with all of this known, it really begs the question, what is going to happen in the future with these glaciers? And for Denman, it's pretty much just a big question mark right now. There really haven't been any studies that have looked into or have modeled Denman's future response to climate forcing. And so we're really not too sure there. For Taunton, there have been a number of studies that have come out that have projected Taunton's evolution. And then one here I've cited is Sun et al. In 2016. They modeled Totten Glacier through 2300 under a slew of different ocean forcing scenarios and found widespread retreat of the entire domain. But such studies used overly simplistic representations of that basal melting process in their ice sheet models. And that didn't resolve, for instance, ocean circulation or on how the subshelf cavity might influence melting. And those are the two primary controls of basal melting. In addition, they've used outdated sets of data sets of bed topography and ice thickness. And so there is definitely some room for improvement there. And so in the research that I completed in my PhD and also what I'm currently doing, the main question I'm asking is, how will these two dynamic glaciers, that's namely Totten and Denman, how will they evolve over the coming century under climate-driven changes in ice shelf forcing? So part one of my talk is going to focus on Totten, which I have boxed in red here. Totten is primarily forced by the ocean. We saw that really strong ocean thermal forcing in that figure. And so I'm going to present some coupled ice ocean model simulations that extend out to 2100 for Totten. The second part of my talk is going to focus on Denman Glacier. Denman is a little bit more complicated because basal melting is driven in part by both ocean forcing and the subglacial water system draining across the grounding line, which I'll talk about later. This subglacial process hasn't been implemented in the transient ice sheet model. And so the first thing we have to do is develop a new numerical representation of that process in our ice sheet model. And then we use that tool to make simulations up to 2100 like we do for Totten. So I want to jump right into part one of my talk, which is going to be based on Totten Glacier. So as we said, Totten Glacier is primarily forced by the ocean. And so if we want to make realistic simulations of the system, we need a way to represent that basal melting process in our ice sheet model. And there's two ways that this can be done primarily. The first is through using a basal melt rate parameterization. And these parameterizations are just simple melt models that are built right into the ice sheet model. They're typically two-dimensional and run on the same time step of the ice sheet model. And so because of this, they're relatively computationally efficient. And they're really great to use for instance, like continental scale simulations or simulations that extend for long time periods. But because they're parameterizations, they also have a lot of simplifying assumptions. Many early basal melt rate parameterizations were just local functions of the of ocean heat at the ice-ocean interface and didn't resolve any ocean circulation. And this was a problem when we started our simulations of Totten because the basal melting wasn't represented well enough to give us a proper ice sheet model. And so early on in my PhD work, I developed a new parameterization that's actually a combination of an ocean box model and a plume model. And so I'll just briefly describe that here. So for the ocean box model, we start with a temperature and salinity value near the ice front, near the edge of the ice shelf, along the seafloor. And the ocean box model computes the transfer of heat and salt along the base of the ice shelf. And this provides us with the full sub-ice shelf temperature and salinity field. So this box model is able to resolve this large-scale overturning circulation within the sub-ice shelf cavity. After we have the subshelf temperature and salinity field, we input that into the plume model. So the plume model, it parameterizes a buoyant meltwater plume that rises from the grounding line all the way along the base of the ice shelf to the point where the plume loses buoyancy. And its temperature, salinity, velocity, and thickness are influenced by the entrainment of warm ocean water from below and the input of cold fresh meltwater from above and on the geometry of the ice-ocean interface. And so we're able to manipulate the equations that govern the evolution of this plume to solve for the melt rate field. And you can see with this parameterization, we're able to account pretty roughly for this large scale ocean overturning, and also on how the geometry of the ice-ocean interface influences melting. And so this parameterization gave us a pretty good match to observations, and also gave us a stable ice sheet model for time. And so that's one way we can represent basal melting in our model. Another way is through coupling our ice sheet model to a dynamic ocean model. And here we use an East Antarctic configuration of the MIT GCM. MIT GCM is a fully three-dimensional ocean model that runs on the time step of 330 seconds, whereas our ice sheet model is two-dimensional and runs on a time step of 2 weeks. So you can definitely see which one's going to be a bit more computationally expensive. In fact, the ocean model is so expensive that it makes it's not really applicable for continental scale runs. But because we're only modeling a basin, it works pretty well for us. And so we couple these models asynchronously, where we run the ocean model forward for 2 weeks, provides the ice sheet model with the basal melting rate field because it solves for the ocean circulation within that subshelf cavity. We then run the ice sheet model forward for 2 weeks to catch up. And then there may have been a grounding line retreat or a thinning of the ice shelf that would influence the ocean model domain. So we alert the ocean model of this change, and then we keep running forward in that asynchronous manner until we get to the end of the simulation. So this figure here describes our coupled ice-ocean system for Totten Glacier. The ice sheet model domain is contained within this black dashed line. It contains all glaciers from Moscow University up through Underwood Glacier, just this tiny glacier here, and extends inland to the ice divide. We have shaded the surface ice velocity in units of meters per year within this contour here. So our ocean model domain extends from 90 degrees east and extended all the way down to 150 degrees east, which is cut off. And we have shaded the ocean potential temperature at 490 meters. And so you can see this really warm water column sitting just off the continental shelf. This is the circumpolar deep water column. This is an intermediate depth warm and salty water mass that is responsible for much of the rapid basal melting of the Antarctic ice sheet. And so this is the water mass we're concerned about that could be reaching Totten to drive that melting. I have a lot of information about the ocean ice sheet model on the right that I'm definitely not going to read, just for reference, but I do want to mention that the base state of the ocean model that we use in our simulations was developed by Nakayama et al. In 2021. We submitted companion manuscripts, and so they developed the base ocean model, provided it to us, and then we experimented on it and ran it into the future. So they were a huge part of this work. And so between our parameterization and our coupled model system, we have the tools now to answer one of our science questions, which is how will Totten Glacier evolve under simulated 21st century ocean forcing? We run our simulations from January of 2017 out to 2100, and we experiment on the system by forcing the ocean model at its boundaries with anomalies in temperature, salinity, and velocity, following CMIP6 high and low emission scenarios. This leaves us with 3 coupled simulations where we have a control where we do not apply any changes to the ocean boundary. We have a low emission ocean forcing boundary scenario, and then a high emission boundary forcing scenario as well. So in addition, we also run 3 companion simulations where the basal melt rate is solved for with that plume box model parameterization. And the ocean temperature and salinities are taken from these 3 ocean models. And the reason we run this is because this allows us to verify how our parameterization is doing relative to the full simulated ocean forcing. It allows us to also understand if our parameterization is missing any key processes and what these missing processes, like the effect that they have on how Taunton evolves over the coming century. And so I want to jump right into some of the time series results here. So in all panels, the time series extends from 2017 out to 2100. And solid and dotted lines refer to coupled and uncoupled model results respectively. On the top here, this is a time series that essentially shows the total integrated basal melting of Totten's ice shelf, right? So we have higher values, that's increased melting. The middle is the mean flow speed of the Antarctic Slope Current. And this is taken along the continental slope just off of Totten's ice shelf. And on the bottom is the ice volume above flotation change. That's just a measure of how much ice our domain has left. And so if our domain loses mass, that's these negative values, that would indicate a sea level rise. So starting at the top here, so we see that basal melting of Totten's ice shelf in the control and low emission scenarios stays pretty steady at about 75 gigatons per year. Whereas in the high emission scenario, melt really ramps up. We see a ramp up after 2055 and then a pretty strong increase after 2065. And this pattern in the high emission scenarios matched really well by a deceleration of the Antarctic Slope Current, which we can see by 2100 reaches almost a stationary state. And so there does seem to be some connection between these two time series here that we're going to explore. In addition, in terms of Totten's sea level contribution, there was two main patterns that stuck out to me. The first is that the coupled models tend to lose mass right out of the gate, whereas the uncoupled models do not, right? So there's this divergence in the mass loss time series that's pretty stark and interesting. In addition, around like 2060 or so, we see this acceleration in mass loss in the high emission scenarios. And then both the coupled and uncoupled model results mirror each other really well here. In total, we find that Totten contributes about 4.4 millimeters to global sea level by 2100 in the high emission coupled scenario, and about 1.3 millimeters in the low emission coupled scenario. So after looking at these time series results, I was honestly left with more questions than answers. The first is that I'm curious as to what the link is between the strength of the Antarctic Slope Current and the strength of basal melting of Totten's ice shelf. I'm also interested in why do we see that divergence in the mass loss results between the coupled and uncoupled simulations right in the beginning of the projection? Then also what causes that turning point in mass loss in 2065 in the high emission scenarios? And I'm going to start with this first question here. And so this is a video from Nakayama et al. In 2021. And so we're looking at a little bit of a different view here. So I'll explain what we're looking at. So on the bottom is the grounded ice sheet. These translucent white patches are the floating ice. So Totten's ice shelf is located right here. And so the continental shelf just off of Totten's ice shelf is right here. And over the open ocean, we have shaded the 552 meter potential temperature, cutting right through that circumpolar deep water layer. And so we are running forward in time. We can see the Antarctic Slope Current transporting water from east to west across our domain. During most of the time, the continental shelf just off of Totten experiences very cold conditions, as you can see here. On occasions, very warm water will flood the continental shelf, and that's what ramps up basal melting of Totten. Let's finish. And so Nakayama et al. Wanted to explore what could be driving these warm water intrusions towards Totten, and if there's any connection between processes going on in the model that we can control. And so what they did was they experimented on the system by warming the far ocean model boundary. They also freshened the eastern model boundary by decreasing the salinity. This would be the downstream boundary. And then they also increased wind stress along the atmospheric boundary. And then so after making this change, they would run the model forward and then see what the on-shelf ocean potential temperature difference is near Totten's ice shelf. And what they found was that warming the far ocean and increasing wind stress didn't really have much of an impact on Totten's, on the ocean temperatures reaching Totten. However, freshening did. When they freshened the eastern model boundary, it had a lot nonlinear increase in ocean potential temperature. And so that's what we see here in this figure, where we have the salinity anomaly on the x-axis and the on-shelf ocean potential temperature difference on the y-axis. And so the main story here is that freshening of the eastern model boundary promoted warm water intrusions towards Totten Glacier. And this is really important in our model because, as I said, we applied CMIP6 anomalies in salinity to our ocean model boundaries. And what we found, especially in our high emission scenario, is a very strong coastal surface freshening signal along our eastern model boundary. And this freshening reached about 0.6 units on the practical salinity scale. So that's about 3 times what Nakayama et al. Applied in their model. And so after 2065, this freshening ramps up, and we believe that this freshening is in connection to what's driving that warm ocean signal near Totten. And so to bring this together with the slope current, I'm going to take some vertical cross sections through 118 degrees east. That's located just downstream of Totten's ice shelf. So we have ice in gray, bed topography is in brown. On the top here, we have shaded ocean potential temperature. And on the bottom is the ocean east-west velocity. And so in our control and low emission scenarios located in the left and middle here, you can see that we retain a coherent Antarctic slope current at 2065. That's when these cross sections were taken. So we have a coherent Antarctic slope current as signified by this blue shading on the continental slope. And this current essentially acts as a dam that holds back this warm circumpolar deep water column from flowing onto the continental shelf. However, in the high emission scenario, you'll notice that the Antarctic slope current is much reduced. And the reason for this that we found is that the coastal freshening would reduce the density contrast between the on-shelf and off-shelf water masses. The reduction of this density contrast would decrease the speed of the Antarctic slope current. That reduces this current's ability to hold back this very warm water mass, which allows it to flow onto the continental shelf and induce rapid basal melting of Totten's ice shelf. And so that's that connection there between not only the Antarctic slope current and melting of Totten's glacier, but also how it's impacted by downstream freshening. I wanted to address these next 2 questions as well, which is why did the coupled and uncoupled mass loss results diverge, and what causes the acceleration in mass loss at 2065? And so to explore this, I'm going to look at patterns of retreat of Totten. And so in this figure here, we have the bed. Bed topography is shaded in gray. We have the ice shelf basal melting rate of Totten's ice shelf is shaded here. And then we have overlaid the 2100 modeled grounding lines, where solid and dotted lines are coupled and uncoupled results respectively. And so in this figure, we have 2 main areas of retreat of Totten. We have the eastern grounding zone, which I'm circling here, then also the southern grounding zone. So retreat of the eastern grounding zone occurs pretty much in all simulations, but the inland extent of this tree is dependent on whether we are looking at coupled or uncoupled results. If we just follow the high emission scenarios, which are in this orange shading here, notice that the coupled simulation retreats a significant distance into the interior of the ice sheet, but the uncoupled simulation doesn't. So there must be some type of process that our basal melt rate parameterization is missing that doesn't allow for retreat of the eastern grounding zone in the uncoupled simulations. And this is not something that we see along the southern grounding zone, right? We only see retreat in high emission scenarios, and the inland extent and spatial distribution matches pretty well between both sets of experiments. To explore this a bit further, on the right here, we have a figure showing yearly modeled grounding lines where red shading is retreat early on in the simulation and yellow shading is retreat later on. We also have bottom ocean velocity vectors in white. And so we notice a very coherent region of oceanic inflow of bottom water into Totten's ice shelf cavity through the eastern grounding zone. This bottom ocean water is going to be that warm circumpolar deep water that drives melting. And so this oceanic heat is first introduced in the eastern grounding zone and drives retreat early on in the simulation. We also notice that the southern grounding zone doesn't tend to retreat until about midway through the simulation, around like 2060 or so. And this pattern of warm water inflow drives basal melt rates that help reveal really what's going on. And so this is a snapshot of basal melting Totten's ice shelf on the left is from our coupled ice ocean model system, and on the right is our uncoupled system from the parameterization. So where we have this region of warm water inflow into Totten's eastern grounding zone, we see elevated melt rates that reach about 50 or so meters per year. So it's pretty strong melting. And if we turn to this same region on our uncoupled model, we'll notice that melt rates are very much reduced. And the reason for this is because our parameterization can't resolve this region of warm water inflow because it doesn't solve for the full three-dimensional ocean circulation. So we are missing this warm water inflow process in our parameterization, and that leads to us underestimating retreat of the eastern grounding zone. And so it's this retreat, the retreat of this sector of Totten that causes that divergence of mass loss results early on in our simulation. And again, the reason for this is because our parameterization can't resolve warm water flowing into the cavity through here. In contrast, we do model the plume of melt rates along Totten's central ice shelf pretty well with our parameterization, although it's a bit overestimated. And because we can resolve this plume of high melt rates, we resolve retreat of Totten's southern grounding zone pretty well. And if you remember from the introduction, the southern grounding zone lies right in the middle of Totten's main ice stream. And so around 2065, when this area begins retreating, that reduces the backstress that this grounding line applies to the upstream grounded ice. Totten's entire ice stream accelerates, and that's what causes that turning point in mass loss at 2065. And so in terms of the conclusions for the Totten work, we have that connection, we found that connection between downstream freshening and how that promotes a weakened Antarctic slope current, which allows warm water to flow onto the continental shelf and enhance melting of Totten's ice shelf. In addition, we also had some results for the mass loss, right? We found that our uncoupled models underestimate mass loss right in the beginning of the simulation because they cannot resolve eastern grounding line retreat. We see a turning point, this acceleration in ice mass loss because southern grounding zone begins to go, and that allows Totten's entire ice stream to speed up. And that's mirrored very well in both our coupled and uncoupled simulations. Okay, so that was the work related to Totten. So I want to jump right into the work that we did for Denman. Denman's a really fascinating system. And so here I have shown our ice sheet model domain of Denman Glacier. Again, we're just to the west of Totten. And so in this domain on the left, we have shaded the bed topography below grounded ice, where blue shading is ice grounded below sea level, and green to brown shading is ice grounded above sea level. One of our collaborators ran a subglacial hydrology model on a domain similar to ours. And so these white contours are where we have fresh subglacial water flowing beneath the ice sheet. And so you can see we have two coherent freshwater channels below the ice sheet, one draining across Denman's grounding line, and then one also draining across Scott's grounding line. Scott Glacier is just this glacier right to the east of Denman. And then over floating ice here, we have shaded the surface ice velocity, and you can see Denman's fast flowing ice stream here. From the introduction, we saw that there is about a 5-kilometer retreat of Denman's grounding line. And the reason that this is worrying again is because Denman is retreating towards this really, really deep subglacial channel. As we said, this is a possible unstable glaciological configuration. And the reason for this is because it could invoke the marine ice sheet instability. This is a term that you've probably heard used for the West Antarctic ice sheet that could lead to collapse of that section of Antarctica, but is also applicable to this system here. And I'll use this figure on the bottom to describe what this is. So this looks kind of like the cross section we took through Amory, where we have the grounded ice sheet on the left, and then the floating ice shelf on the right. Now, and these dotted lines refer to grounding lines during different stages of retreat. And so the marine ice sheet instability is invoked when the grounding line is retreating down a retrograde sloped bed. And that just means that the grounding line lies on a bed that's deepening inland. And so this could lead to runaway retreat of the grounding line. In addition, notice that at every stage of retreat, the ice thickness at the grounding line is increasing. And so because of that, that also means that the sea level contribution from the glacier will increase progressively as retreat ensues. And so it's this combination of runaway grounding line retreat and an enhanced sea level contribution that has the glaciological community worried. And so this is a cross-section taken through Denman's bed topography, where we have the depth below sea level on the y-axis, and then distance along the flow line on the x-axis. And so Denman's grounding line is designated by this gray vertical line, and it's retreating to the right. And so you can see that the bed that Denman Glacier is retreating on is extremely retrograde. There may be some stabilizing features along the way, but for the most part, it's all downhill. And you can also see the ice thickness increases drastically as well. The grounding line, the ice thickness is about 1.2 kilometers. And at its deepest point in this subglacial trench, it could reach about 4 kilometers thick. And so that's why this glaciological setting for Denman is possibly unstable. And so because of this, it's really important that we're able to properly model how this glacier might evolve over the coming years and decades. And so in this figure here, this is showing the surface ice velocity of Denman Glacier, where you can see a very coherent ice stream. Here's the grounding line, and this is the floating ice tongue. And what I want us to really focus on are these ocean temperature observations that were taken by tag seals just near the terminus of Denman. The highest ocean temperature reaches about negative 0.7 degrees Celsius. And this is relatively low compared to the ocean temperatures that are observed along the rapidly melting West Antarctic Ice Sheet. Ocean temperatures there can reach about 1 degree Celsius or so. I think that's what they've been observed at. And so that's significantly higher than what we're seeing near Denman's ice tongue. However, basal melt rates right near Denman's retreating grounding line are the highest across any other ice shelf in Antarctica. And so this is an enigma, especially for ice sheet modelers trying to work with this domain, because the current generation of melt models uses ocean temperature. Well, they compute melt as a function of ocean temperature. And so this ocean forcing is way too low to be able to resolve the melt regime of Denman. And so it points to the fact that there's probably some other process that is enhancing melting right near Denman's grounding line. And so this is the current view of most melt models today, where we have some type of input ocean condition that drives melting of the entire ice shelf. But what we hypothesize might be going on is that there is fresh subglacial water that's flowing between the grounded ice sheet and the bedrock. Now that deep channel that Denman Glacier is retreating back to, we believe it's topographically primed to vigorously channelize this fresh subglacial water system and direct it directly towards the grounding line. Once it gets to the grounding line, it will eject into the sub-ice shelf ocean cavity, and it can increase convection of this near grounding line water mass, which would enhance melt rates. This process is theorized to be occurring along West Antarctica as well. This is from a study we did all in 2020 of the Getz ice shelf. And so in this figure, they have the modeled subglacial freshwater flux beneath the grounded ice sheet on the bottom. So you can see some coherent channels flowing into the sub-ice shelf ocean cavity, which is designated by this blue to red shading. This blue to red shading denotes the melt rate difference between observations and melt rates that are parameterized with a melt model that doesn't account for subglacial discharge. So where we see red shading, this denotes melt that is influenced by subglacial discharge. And you can see that we see these melt rate enhancements pretty close to where we have these subglacial channels draining across the grounding line, right? So this is a pretty localized process. And so this melt rate enhancement process by subglacial discharge hasn't been included in ice sheet models. And so, but we believe it's pretty important to Denman's evolution. And so if we want to properly model Denman, we need to include this in our ice sheet model. And so we need to be able to, so we develop a parameterization to do this. And so the base of our parameterization is that buoyant plume model that we discussed in section 1. And so, and again, this plume, it models a buoyant plume rising along the base of the ice shelf, where the plume has a temperature, salinity, velocity, and thickness. Now you'll notice as we approach the grounding line, the thickness of the plume is going to also approach 0. And so what that means is that the grounding line, there's no plume to induce melting. And so at the grounding line and within the first few kilometers or so, melt is also going to basically be 0 as well. But this assumption fails when we have fresh subglacial water draining across the grounding line. This subglacial outflow will enhance this entrainment factor here. It will draw more warm ambient water into this grounding line water mass, which will significantly enhance melting. Work by Jenkins in 2011 and Donald Slater in 2016 found that melt rates scale to about the 1/3 power of the discharge flux within this region. Jenkins in 2011 actually came up with an analytical solution for the melt rate field there. And so the way we comprise our parameterization is that within this near grounding line water mass, where melt rates are primarily driven by subglacial outflow, we used Jenkins 2011, their analytical solution. Beyond this distance, where ocean dynamics are the primary driver of melt, we use the analytical solution from this buoyant meltwater parameterization. I don't want to get too into the weeds with the math there, but that's just generally how this works. And I wanted to jump into some of the melt rate results that we found here. In all panels, we have the bed topography below grounded ice is shaded in gray. The subglacial discharge flux is in this white to purple shading. And you can see in each panel, we have a very strong freshwater flux crossing Denman's grounding line. We also have a weaker diffuse channel model that flows across Scott Glacier's grounding line. Along the floating ice, we have shaded the basal melt rate. On the left is the modeled melt rate from our parameterization. In the middle are satellite inferred melt rates that were averaged between 2010 and 2018. And then on the right here is melt rate difference, which I'll get into. But in general, our melt rate parameterization does a really good job at matching the spatial distribution and magnitude of melt near Denman Glacier's grounding line. And this was something we were never able to match before without including that subglacial process. And so we were pretty happy with the results there, especially because we used those ocean temperature observations from the tag seals, and we were still able to get a good fit here. So this figure on the right, this is showing the modeled melt difference. So this isn't the difference between these two panels. This is the difference between melt rates computed with our parameterization that do and do not resolve subglacial discharge. So this basically tells us what the subglacial discharge contribution to melt is. And for Denman, it's about 60 meters per year. So what that means is that subglacial discharge contributes about half of the melt signal near Taunton's grounding line. And for Scott, it's much reduced. And that's again because this channel is pretty diffuse and weaker, much weaker when compared to the one flowing across Denman's grounding line. And so now that our parameterization has been validated, we can begin answering this science question for Denman, which is, again, how will Denman Glacier evolve under simulated 21st century ice shelf forcing? And I think more specifically, what we're interested in this study is determining the relative impacts that subglacial hydrology and ocean forcing play on this glacier's evolution. And so we run simulations that are very similar to what we ran for Totten, run from 2017 to 2100. We take the ocean temperature and salinity from those 3 ocean models that we developed in the last section, where we have a control, low, and a high emission. And then we run 2 sets of experiments, models where we do resolve that subglacial melt enhancement process, and then models that we do not. And again, the reason for that is so we can tease out the relative impacts that ocean and subglacial hydrology forcing have. And so just like for the Totten models, I wanted to jump into some of the time series results. where on the top, this is the total integrated basal melt rate for Denman and Scott's ice shelf. And then this is the sea level contribution time series here. And then the dotted and solid lines refer to the models that do not and then do resolve subglacial discharge. So solid lines are where we resolve subglacial discharge. And you can see we pretty much have a very similar pattern to what we saw for Totten, where after 2065, melt really ramps up. And and we already know because we're using the same ocean model that that's due to an Arctic slope current weakening that ensues. But I think the main idea we want to get across here is that we really don't see any difference in the total integrated ice shelf melt of Denman and Scott. But we already know from the previous slide that the subglacial discharge contributes about half of the total melt signal near Denman. And so what this points to is the fact that like if we just look at basin averaged and basin integrated values, we're not going to notice how subglacial discharge enhances melting, right? This is a very localized process. So we need to look locally towards the grounding line to see any significant changes. In terms of the sea level contribution, we do see an enhanced sea level contribution from Denman and Scott in the subglacial hydrology runs, where it increases sea level contribution by about 1/4 of a millimeter by 2100. And the sea level contribution also accelerates after 2065, which I'll get into on the next two slides. The sea level contribution results from retreat that the domain undergoes. Here we have, similar to that Taunton figure where we have bed topography in gray, the basal melt rate is shaded in this red shading, and we have overlaid the 2100 grounding lines. And you can see that there is retreat of Denman and Scott Glacier. Scott Glacier has a lot more widespread retreat, and the inland extent is a lot greater than that of Denman. You can also see there's the dotted and solid lines. Grounding lines are basically superimposed, meaning that there doesn't seem to be much of a difference that subglacial discharge has on retreat of the system by 2100. You do see a little bit of a difference for Scott here, where the models that had that subglacial enhancement process retreated a couple of kilometers inland. Overall, the difference doesn't seem to be too big. But to explore this further, I'm going to zoom into these two boxed regions and look at some snapshots. So in the middle here, we zoomed into Denman Glacier. On the right, we zoomed into Scott. And on the top here, we took a snapshot at model year 2035. And on the bottom is a snapshot at model year 2064. And so for Denman Glacier 2035, the models that resolve subglacial discharge retreated back to a stabilizing feature at this time. And you can see that the models that did not have that subglacial enhancement feature do not. And in fact, the dotted grounding lines don't reach the solid grounding lines until about 2064. And so what this points to is the fact that subglacial hydrology accelerated retreat of Denman Glacier by about 30 years. And that's significant within the context of Denman's glaciological setting, which I'll talk a little bit about more on the next slide. For Scott, the picture doesn't change too much from what we see in the basin view, right? The subglacial enhanced grounding lines are a few kilometers further inland than the dotted ones. And so again, subglacial discharge does accelerate retreat a little bit for Scott, but it's definitely not as pronounced as for Denman. In the next slide, I'm going to take some vertical cross sections through Scott Glacier, through Denman and through Scott as well. And that's what's shown here. So we have Denman on the left, Scott on the right. We have ice in blue, the bed topography is in brown, and then each of these vertical lines corresponds to the position of the grounding line, the color of which corresponds to the year of the simulation. And for Denman Glacier, we said that there is retreat back to a stabilizing feature by 2035. And that stabilizing feature is this 10-kilometer section of prograde bed topography. And prograde is just where the grounding line is retreating upslope. Denman's grounding line stabilizes on this 10-kilometer section for about the last 67 years of the simulation. It endures melt rates that reach upwards of 200 meters per year. And so this is an extremely stabilizing feature that's protecting Denman from retreating back into this really deep subglacial trench. And we computed that if the late century retreat rate were to be sustained, that Denman Glacier would retreat back into this subglacial trench by about 2150, so the middle of the 22nd century. And then when it does, Denman's sea level contribution will be about 1 millimeter for every 5 years of retreat. And so understanding that this subglacial melt enhancement can push Denman towards this tipping point by a couple of decades is important because again, Denman's sea level contribution will really ramp up. And so it's good to know when this might happen, that subglacial hydrology can push Denman closer and closer to that point. For Scott Glacier, the picture is a little bit less interesting. We don't have a lot of stabilizing features for the grounding line to retreat back to. So you can see retreat happens pretty steadily throughout the entire simulation. There's actually a little area of retrograde bed topography where Scott speeds up. But overall, just continued retreat that extends about 30 kilometers inland. And this large scale retreat comprises the majority of the domain's mass loss after 2065 that we saw in the time series. And so in terms of the conclusions for the Denman work, so this is a little video on the right, just showing the evolution of the domain in the high emission subglacial hydrology scenario. And I'll just read off some of these here, where first we modeled these really coherent subglacial channels draining across Denman and Scott's grounding line. We developed a new parameterization of ice shelf basal melt that can resolve that subglacial enhancement process. And with this, we were able to resolve Denman's high degree of melt while using realistic ocean and subglacial boundary conditions. We also found that the impact that subglacial discharge has on glacial evolution is very nuanced, right? We have to look locally to where this process is occurring to see any change in the domain. In terms of the research that I'm going to continue doing here at IGPP, so Jamin and I submitted a proposal to NASA, and we're funded to work on 3 dynamic systems along Antarctica. So we're going to do some work on Thwaites Glacier. That's the so-called Doomsday Glacier on the West Antarctic coast. Also going to continue doing work on Denman and also on Cook Glacier located down here. We're hoping to model each of these 3 glaciers by coupling our ice sheet model to both an ocean model and a subglacial hydrology model. So we'll be able to accurately represent the forcing striving change of each of these systems. And then in addition, we're also hoping to do some field work. So each of these black lines is a ship track that shows where oceanic observations have been taken. And we're hoping to fill some gaps near these glaciers that are pretty data sparse. And this will be really important in initializing and validating our ocean model for each of these 3 regions. Just want to give a big thank you, especially to my collaborators and my funding sources. It was a massive effort with a lot of this modeling work, and so all the help was extremely appreciated. And I'd be happy to answer any questions that anyone may have. And thank you so much for listening.
Thank you, Tyler. That was really interesting. A lot of information. We have about 4 minutes for questions. If anyone has a question, feel free to raise your hand in the chat or just unmute yourself and pipe up. Chloe.
Really awesome talk, Tyler. Lots of cool and exciting things. I was kind of curious just about the last slide you showed about the future projects and like the data that you'll be collecting. You mentioned temperature, like ocean temperature data, but I was wondering if there's anything else that you guys will be doing and like how you think that's going to help your modeling.
Yeah, so I believe we'll primarily be doing oceanic observations. I think there'll also be some There'll be bathymetry observations as well along the coast, which will be really important because that's really what determines where that warm water is steered to. And that's also just it's a pretty big unknown in our ocean models as well. So those bathymetry observations are going to be super helpful.
Awesome, thanks.
Yeah, thanks so much.
I follow up on the bathymetry comment. You're talking about marine gravity stuff or real bathymetry obs?
So I believe Senator Jamin is really the master of this stuff. I'll try to give my best answer, but I know that when we deploy CTD and AXBTs, when they hit the ground, there's a certain signal that we can get that we determine the bathymetry from. And so I believe we'll be able to get bathymetry measurements from the deployment of those ocean sensors. So they'll be like spot measurements.
That's airborne.
Airborne, yes.
Yep. Okay. I'll ask another question. So you mentioned the freshening downstream.
Mm-hmm.
Is that what you meant? That you're talking about to the west of Totten? Or
yeah, so like Totten is right here, and our eastern model boundary was right about here. And so the water masses are transported by the current flowing from east to west. But yeah, it was downstream right about here.
okay, I'd call that upstream. So that's why I got confused.
I think you're right. Yep. Sorry about that.
Okay, so you're imposing the freshening at the eastern boundary, and then the slope current is taking it downstream to Totten.
Yes, yeah, exactly.
Okay, good.
Jamin.
Thanks. Yeah, Tyler, fantastic presentation. I just wanted to provide a quick follow-up on Lori's question. The idea is to also combine those spot measurements that Tyler mentioned with airborne gravity observations. So we can use the spot measurements as constraints on the forward model, basically, and for those gravity inversions, because we have no information on the density of the seafloor. And so if we have those spot measurements, we can combine those with the gravity to improve those forward, so we have better constraints. That way we can eliminate those big offsets in bathymetry that have been shown to be caused by uncertainty in density.
So how many toys do you have to throw out the window?
Well, yeah, I mean, so we have about 40 per year provided by the US Navy, and then we are trying to buy some additional sensors as well. So, but for each target, we should have at least a dozen. For the Thwaites this year, we deployed 29, for example.
Did you need them for Thwaites? Because that's fairly well surveyed, right?
Well, we were deploying them in areas where the ships haven't gone before. So yeah, where we can, with the airborne platforms, we can get to some spots that are otherwise tough to get to without underwater robots. And again, great presentation, Tyler.
Thank you so much.
Yeah, agreed. Let's thank Tyler one more time. We are at the canonical hour. So that's it for this term. Thanks everybody for joining us. And we'll again get the schedule, the lineup for next term out to you in the upcoming days. And don't forget to send us, John Hua and I, your recommendations for next year's seminar speakers as well. Thanks everybody. We'll see you next term.